Hi there. In the last video, I left you with the problem 2 to the power of x equals 5. What is x? Knowing that x can't be a whole number, right? Because 2 squared is 4 and 2 cubed is equal to 8. And so x must be between 2 and 3, sorry, but we don't know what that value is. Now, I asked you to think about how you might solve that using trial and error, and the answer is maybe using a calculator like so. And you can see that I've just gone up in 0.1 increments here from 2 to try and work out what it is, and got to 2 to the power of 2.3 and got 4.9, which is close, and then 2 to the power of 2.4, which is 5.27, which is too far over. So it must be between these two values, so maybe pick the midpoint, 2.35, and that gets me 5.09. So it's got to be less than 2.35, but it's got to be above 2.3. I could keep trial and erroring it until we get some sort of 2 or 3 decimal places answer. Secondly, another approach would be to maybe draw the graph of y equals 2 to the power of x, which is what I've done here on the blue line, and also draw the graph of y equals 5, which is the red straight line. And the point of intersection must be where 2 to the power of x equals 5. And then I could use my menu, analyze graph, and then intersection, and that would give us 2.32 based upon our GDC, which is to 2 decimal places at least, which is a lot faster than trial and erroring it, but still not too, there's a bit of work there just to get that, and there's got to be an easier way, right? And of course there is. So let's have a look at that. What we're really saying is 2 to the power of x equals 5. What does x equal to? And in this video, I'm going to cover the basics of how we go about solving that kind of problem. Just the basics of the fundamentals of this idea called logarithms. In the second video, I'm going to go through some examples of solving problems using logarithms. And in a third video, which I'm not going to make compulsory, but is good, is that we're going to have a look at some log laws. Okay, so let's have a look at this. Usually when we think of operations like addition and subtraction, we can consider a triangle here to represent the relationship between the operations between numbers. So for example, if I have 2 and 3 as my base of my triangle here, if I add these two numbers together, then I get 5. So in other words, the base here, 2 plus 3 equals 5. Great. It's also reversible. 3 plus 2 is equal to 5. But if I want to go from the apex of the triangle, the top of the triangle, down to the bottom, I just do an inverse operation, right? And the opposite of addition is subtraction. So if I go minus here, 5 minus 3 is equal to 2, or 5 minus 2 equals 3. So the downways operations from the top to the bottom could be considered like so. 5 minus 2 equals 3. 5 minus 3 equals 2. When we have a look at exponents, though, as a function, it is different. Because although the bottom works nicely, 2 to the power of 3 equals 8, we certainly can't reverse it. 3 to the power of 2 equals 8. That doesn't work. 3 squared is not 8. And going backwards doesn't work as well either. If we're going backwards here, we would say we would use the nth root operation. So the number is 3 here, so this would be the cube root of 8, which is equal to 2. So that's fine. But if we used an nth root operation down this way, we would have the square root, because there's a 2 there, the square root of 8, which is not 3. So the operation to go here is not the same as the operation to go here. Okay, so we need to effectively invent a new operation. Okay, down here, what we're really doing is we're asking ourselves, x cubed equals 8, what is x? We cube root 8 in order to get what x equals, which is 2. Here, we're saying 2 to the power of what equals 8? We know it's 3. So the opposite operation we're going to define using this word called log, which is short for logarithm. And we're going to say the opposite operation in order to work out the power, the exponent, is to take the logarithm of the answer. Okay? So instead of cube rooting the answer in order to get the 2, we're going to take the logarithm of 8, and the logarithm of 8 will give us the 3 that we're looking for. So we'll see this in operation, and then we'll go through some examples. So this is how we define the logarithm. We say in general, if x is equal to some base a to the power of y, then we define the power as equaling log base a x. Now this is really important to note that if I have x equals 2 to the power of y, then I'd have log base 2x is equaling y. If I had x equals 3 to the power of y, that would be y equals log base 3x, and so on. So you're going to have a whole series of operations depending on what the value of a is. Okay, quick word on notation. So this could be, so if a equals 2, log base 2x, a equals 7, log base 7x, a equals 1.5, log base 1.5x. That's how you'd write it. If you remember, there are some occasions where we don't write in a number because it's called implied. So if you see x by itself, it's implied that the coefficient is 1. 1 times x is x. If you see root x like this, it's implied that it's the square root of x. We don't write the 2 in because it's so common. Logs have the same sort of thing. So if I have log base 10 of x, brackets are not necessary, but I put them in, that's the same as log of x. Okay, so the 10 is implied. So just remember that as we go along. Okay, so we have this concept. The reason why it's useful is because we can then use a calculator frequently to solve the problems, and we'll look at that towards the end of the second video. It also means that because these are all wrapped up in powers, we're able to create some laws that allow us to manipulate logarithms. And I'm going to do these on the next slide here. The summary is on page 453 in your textbook, but there's your 3 basic laws there. Okay, so if I've got 2 things multiplied together inside log, it's log base am plus log base an. If it's m divided by n, then it's log base am minus log base an. And if it's log base am to the power of p, it's p log base am. And we'll look at some examples which use these laws to simplify logarithms. There are 2 results that come out of logs. One is log base a1 equals 0. That kind of makes sense, I hope, in that if we rewrite it, base to the answer 0 must equal 1, and anything to the power of 0 is equal to 1. And again, if I go a to the power of 1, it's got to have to be equal to a. So that's where those 2 solutions come out. Now, I know this is a very quick video to explain the logarithms. These log laws here, they look very similar to your power rules or your exponent rules, I hope. You know, a to the power of m plus a to the power of n equals a to the power of mn. There is definitely a relationship between power laws and log laws, which is why these look like this. I will produce a separate video which explains the log laws. It's not compulsory viewing, but know that if you watch them, it'll probably help cement why these laws work. But in the next video, we're simply going to have a look at a bunch of examples which use these log laws to simplify or to solve things without a calculator.